Yeah, hello, welcome to Haskell. Yeah, I was looking at Nix this morning a bit. Now I was watching the Nix hour exploring Nix packages lib, which is kind of a like a functional Haskell like library in Nix packages. And in Infinite will talk of types, order of. And why am I saying this? This just comes back to the to learning the language and how to express yourself. How to express this function application. Like check this: a set of elements of type element type ordered according to the given partial ordering function before, equivalent to a yeah. This I still don't understand. The result of this type is a list of items. Oh, the result of this type. So the type of a function. So it takes some arguments of some type and outputs results of some other type. So results of this type is a list of items ordered according to the replaceable before replaceable function. According to the before function, if there are multiple possible orderings, an arbitrary one of them is chosen. Here is a simple example. Yeah, why am I reading this? Because words are important in functional programming. It's almost like when you explain something, it has to type check. It has to type check, yeah. Yeah. I wanted to show also this. Yeah, sometimes I read this. I don't know if I even said this already in the past video. Probably. Probably. If you want to enter the stateless Zen, the Zen of stateless state, the Zen of stateless state. I think that's the lecture of Brian Beckman. A function is a mapping that takes one or more arguments and produces a single result and is defined using an equation that gives a name for the function, a name for each of its arguments, and a body that specifies how the result can be calculated in terms of the arguments. Now, it may be that I'm just going too deep with this. It's possible. You could get lost in this. Like you could actually almost like, meditate on the meaning of this sentence. Yeah, the best would be to take an example. Okay, not to get lost. The best would be to take an example and be able to express in words what the code does, but to have some kind of a uniform way of describing how functions work. So not that each time when you describe a function you use a different kind of set of words, or you say a little bit like this, a little bit like that. I think that doesn't really help with understanding. So it's almost like you have to have a train, you have to have the trained vocabulary and and um and how you describe things. It has to be in a similar way, because once the functions start to take all kinds of meta rules, if you're not clear with this, I think it's just going to be a mess. Oh, this is why functional programming matters. All right, let's go again with the conditional. We're going to make a function that there's also one interesting thing. Interesting next. Yeah, interesting next. I think it was I should have saved it. It's interesting how Eric Mer describes, I think that kind of helps also, how he described Eric Meyer, functional programming, how he described conditional expressions. Ah, oh, I have to find a chapter. Oh, that's not, I think that's fundamental. Wait, add Boolean, chapter 2. Maybe it's this, actually. Maybe it's this. I don't know if it types and classes.
All right. Well, welcome everybody to lecture 3 of the series in functional programming. I assume everybody has gotten their books types by now. No. The discount you get.
This should be here. Yeah, this is kind of, wait, ML, Prelude, Haskell expressions, take and drop.
So now that we have all the questions of lecture 1 out of the way, thank you, by the way, for all your fantastic questions.
Numbers, syntax,
let's move on to chapter 2. And chapter 2 question here that, you know, you either use a list. Now, back to syntax, we talked enough about semantics or scheme or whatever, and there's you know, let's like even
yeah, maybe it's better if I prepared this. Wait, yeah,
fact
I can
whether
stop.
You know, this thing starts with a lowercase or uppercase.
I can stop the.
So here's the layout.
I can stop
rule.
this
so
and then
in
I'll
Haskell,
find
I can
it.
write this.
All right, I found it. What's this?
The way is, you know, abstract from the specific. Wow, what a word! I have to get started here. To abstract from the Haskell syntax and see, you know, how these things will look like in other languages. So let's define a simple function. So this is the function that takes an integer to an integer and takes the absolute value. Again, you know, we're not trying to define any meaningful function, it's just to illustrate the syntax. So in Haskell we write this as follows. So you define first the type, as we have seen last time, abs double colon int arrow int, and then we define the function straightforwardly as you expected with a conditional. So if n is greater than or equal to 0, then it's n, and all otherwise it's the complement of n. And of course, you know, well, of course, you don't write, you know, the kind of greater equals like this, but you use the ASCII representation. But for the rest, this is kind of, you know, as close to concrete Haskell as you can get. And again, you know, this doesn't look kind of that different from, say, C#, except that it's one thing that I want to emphasize, that in Haskell, you know, we separate the type specification. So the type, which is like int arrow int, from the function definition itself, you know, abs of n equals that big expression. Whereas if we would look, and I'm trying to use a different color here, if we would write the same function in C#, you know, or let's use VB for today. You know, in VB we would write function abs n as int as int. So in VB or C#, you kind of intermingle the function definition and the type definition. So, you know, there's the type and the function are kind of intermingled. Interesting thing about VB syntax, which I personally quite like, is that in VB you put the return type, you know, here as an s, whereas in C# you would put the return type in the beginning of the function. So in some sense, the VB syntax is much closer to the kind of, you know, mathematical syntax here that we use in Haskell, where the arguments kind of, you know, the types of the arguments are given first, and then you end with the type of the function itself.
This is cool because he will come to a point where he's saying like the conditional expressions are, they kind of intermingle. Well, it's still the same type, right? But it's kind of the functionality and the operators are kind of intermingled within a line of sorts, like within the whole line. They're not like separated, you know, like here are the types, or like here is the interface of the function, and here is the data, or maybe that's a okay.
And of course, like any other construct, you know, you can always compose things. So like in this function that gives you the sign of a number, right, where there's a nested conditional. So it says if the number is less than 0, then the result is -1. If the result is 0, then it's 0, else it's 1. In Haskell, there's not the kind of classical if, then, else if construct. It's just you put another conditional inside the else part.
Wait, can it?
In Haskell, the result is.
So there are two ifs. If this, then this. Else, if this, then this. Else one. I see. So if we even let's do signum n is, yeah, if n is less than 0, if n is, no, if n, right, signum of n, if n is less than signum gives a sign, right? If n is less than 0, then minus n, then -1. Oh, then I don't know what actually is signum. Then -1. All right, else. Then we need if n is greater than, right? Equal than 0. All right, we need all the options. Is equal than 0, then 0. Yes. Else, now we don't have to put if n is greater than 1, because that's the last remaining thing, right? Else 1. So this should work. Signum 12, 1. Signum -12. Signum -12. Haven't applied a function to enough parameters. It could be signum like this. Yeah. Yeah, now it works. You need to put it the minus in parentheses. Signum, and then signum 0 is 0. It just gives, oh, it just gives like a sign. -1 + 1. Okay.
0, then it's 0, else it's 1. In Haskell, there's not the kind of classical if, then, else if construct. It's just you put another conditional inside the else part. And then what we refer to here in the ambiguity with nested conditionals, that's an interesting kind of research exercise for homework, is you look for the dangling else problem. So this is a problem, a syntactic ambiguity that languages like Pascal have, where if the else part is optional, you can get into syntactic ambiguities.
Okay.
And most, I think maybe C also has that same problem. But again, that's just a parsing issue. All right. Now back to lecture 1, where we said in Haskell we put a lot of effort in making our code look as concise and as beautiful as possible, and to make it look as close to mathematics.
So yeah, he was saying here like while if then while the if then else conditional somehow puts all of this, I don't know how to express it, like in a one sentence of sort. Here with guarded equations, it's kind of, there is a the functionality itself is kind of separated, right? You have something here and something there, so it's kind of the layout is a bit different. All right, let's just get back to this. This was kind of interesting. These are wonderful lectures, but they begin kind of differently. They follow the programming in Haskell book from Graham Hutton, which is a great book, really a great book. But it's kind of, it's not like wordy like this or like me. I'm saying it's like, yeah, it's like even the book, you could put the book inside of the GACI and it would compile. Like you could just load the book, load Graham Hutton book, and it would output like the result. It's that good, yeah. It's that good. That's the book. The book. Wait, this is why programming Haskell. Yeah, yeah. That's the guy who writes like a function is a mapping that takes one or more arguments and produces a single result. Let's zoom in, and is defined using an equation that gives a name for the function, a name for each of its arguments, and a body. It specifies how the result can be calculated in terms of the arguments. And then he takes an example. And then he's wonderful. It's incredible. Even like, look at this introduction. In this chapter, we set the stage for the rest of the book. Bam. So he first sets the stage for the rest of the book. It sounds like Haskell code, right? Like you even have the rest. We set the stage for the rest of the book. It's like, of course, there is the rest of the book. It's almost like someone would say, we set the stage for the rest of the book. He's like giving the information even in the first sentence of the rest of the book. We get the head of the rest of the book. We start by, now he goes again from the beginning, right? How is he going to do it? We start by reviewing the notion of a function, then introduce the concept of functional programming. I guess notion and concept are, what does he mean by that, right? Because he's careful with words. I kind of like that. Even so even if you don't understand, like you need to unpack. Like you understand it, but you need to unpack sometimes how he, right? We start by reviewing the notion of a function, then introduce the concept of functional programming, summarize the main features of Haskell and its historical background, and conclude with 3 small examples that give a taste of Haskell. So this is the whole first chapter. But it's like even AI cannot summarize like this. All right, let's go. Let's start. Let's continue, right? Double small number. Did I do this even? No, I didn't. Signum, all right. Double small number. Now we're going to make a function that multiplies a number by 2, but only if that number is smaller than or equal to 100, because numbers bigger than 100 are big enough as it is. But we are still working with values. There are no types here. I guess someone would criticize this book because it starts like this. It's almost like a big lie. No, it's not a lie. I think it's good this, especially for someone who has some experience in programming. This may be like, but even not. Like maybe types are. Yeah, I like to start with types. I like types, and it's kind of like, but yeah, let's just do double small number x. That's a long name. Double small number x. If x is greater than, what did we say? If that number, only if that, but you see how he words it, that we're going to make a function that multiplies a number by 2. So he says the result. We're going to make a function that multiplies a number by 2, but only, and then he says the condition, but only if that number is smaller than or equal to 100. if greater. Oh, you see the wording? Only if that number is smaller or equal to 100, or equal, because like, because numbers, yeah. So you see, we're gonna make a function that multiplies a number by 2. Yeah, you can't do like x times 2, right? If only if that number is smaller or equal to 100. If x is smaller or equal to, this is wrong, but I'm just saying what I hear. Double small number x is x times 2 if x less or equal than 100. X times 2. If x greater than 100, then x, else x times 2. You see? Right? No. Okay, I'm not supposed to be stuck at this part now for this long, but it's kind of interesting how you phrase things. We're going to make a function that multiplies a number by 2, but only if that number is smaller. So he puts the conditions at the end of the sentence, but only if that number is smaller than or equal to 100. But only if that number is smaller than or equal to 100. But only, now I'm interesting. How did Graham, I will make a pause now, and I'll check how Graham described the conditional one. I'll check that. If there is an example that is similar to this one, it would be interesting to check the wording. All right, I'm here. So it's interesting that he talks about conditional expressions in the 4th chapter. And the 3rd chapter is on types. He introduces some types and instances of types. And in the 4th, right? Look. In the 4th, he talks about conditional expressions. So Haskell provides a range of different ways to define a function that choose between a number of possible results. So these are functions that choose between a number of possible results. The simplest are conditional. So, okay, so it's kind of like this is the simplest case, right? The simplest are conditional expressions. So there's a range of different ways to define the function to choose. And the simplest are conditional expressions, which use a logical expression. So he already introduced the bools. We kind of all introduced it with true and false, okay? Which are logical expressions called a condition, which use a logical expression called a condition to choose between two results of the same type. Okay, that's nice. The simplest are conditional expressions which use a logical expression called a condition to choose between two results of the same type. So it's nice how he says the condition is a logical expression. What's a condition? A logical expression. Yeah. If the condition, like, you can almost tell that he can program in Haskell. If the condition is true, so now he continues from this, you see, it's like he expands from this. If the condition is true, then the first result is chosen. And if it is false, then the second result is chosen. Yeah, but still, if the first condition is true, he doesn't say, he doesn't say if the first condition is true, then the first result is chosen, right? If the condition is true, then the first result is chosen. And if it is false, then the second result is chosen. So there are two results and one condition. And if the condition is true, then you choose the first result. And if it is false, you choose the second result. For example, the library function absolute, right, that returns the absolute value of an integer, can be defined as follows. abs is a type. Abs is a function, right? It takes an argument of type int and gives the result of type int, right? It's an absolute number. Do we have already abs defined? Do we have? Wait. Oh, did it? Oh no, it's going. Oh, sorry. Lambda expression. I thought I'm going. Okay. Abs n is, if n is, this is one more thing. Yeah, he says here if number is smaller than or equal. So does that mean that you have to put any equality sign along with this? Smaller than or equal to 100. No, it's not, because it's smaller than or equal. That's why he does if x is greater than 100. He doesn't need the equal sign. Yeah, that's one more thing that we missed. If n is greater or equal than 0, then n, else minus n. So the condition is this, and then the first result is this, and the second result is this. So let's get back to our, if the condition is this, if the condition is x is greater than 100, only if that number is smaller than or equal to 100. Yeah, this is confusing. This is confusing because he used a different condition. I'm sorry, but this is confusing. He used a different. I have to check with him. Someone wrote on Twitter like a comment that liked the video, and he said that he works with him. But he did, yeah, okay. He did say like he's. I don't know if he maintains like low profile or something. Maybe I shouldn't talk about it. Okay, anyway, maybe I should check with him. Maybe I should check with him. No, I don't have to check this. No, it's just, but it's, I don't have to call people so don't call people like, hey, you, how did you name that function? You know, don't do that. No, it's just my intuition is kind of, this may be confusing because, yeah, let's check again. The library function ab that returns the absolute value of an integer can be defined as follows. If the condition is true, then the first result is chosen. So it's like the condition. So that's the condition, if the number is smaller than or equal to 100. But he expressed it with x is larger than 100. So it makes sense, right? Because it makes sense, right? Because if you write x is larger, let's x is larger, wait, you could like 101, you see, wait, 100 is larger or equal than 100. True. So you see, and yeah, and if it's like 99 is smaller or equal than 100, true, right? But only 101 would not work. No, of course it's true because it's larger or equal than 100. Now I'm confusing again, right? I'm going to make a function that multiplies a number by 2, but only if that number is smaller than or equal to 100. So if this number was smaller or equal, can we like write this condition? All right, yes, okay, right. Double small number x is what? Okay, if, let's rewrite this. if x is smaller or equal to 800 that multiplies a number by 2. Okay, that's the result, but only if that number is smaller than or equal to. So first we should have a case where this does not happen, right? It's like if you give me an empty list, then I'm just going to give you back an empty list. So like the first case is the fail, I guess. But multiply, and this will come as the second one. Or maybe we should put this, yeah, when do you put this? Should you put this as the first result? What does Graham says? If the first is true, then, if the condition is true, then the first result is chosen. And if it is false, then the second result is chosen. So if abs, let's see abs, how is defined? N is, if n is greater than 0, then n, else minus n. Yeah, but this is not the same, right? Because it's like the false condition is just the same as the true condition. I mean, it's kind of, you know, what's the absolute value of a number? If you give it like a minus, it's going to be plus. If you give it a plus, it's going to stay plus. But this is kind of a different, so this is kind of involves some kind of operation. So we're going to multiply it by 2, otherwise we are not going to do it. So is this false? Right. If x is smaller or equal than 100, only if that number is smaller than or equal to 100, it's going to multiply by 2. Okay, then x times 2. X times 2, right. Okay, now it's clear. Double small number x is a function that takes an argument, and if that argument is smaller or equal than 100, then it will multiply that argument by the number 2. Else, it's going to just return the x as it is. Is this going to work? So let's do double small number. 3 is 6. So it doubles the number. Ah, he wrote, you see, he wrote if the x is greater than 100, then do nothing. All right. So if we give it like 145, it's just going to give us the x. Else, so if it's smaller, then do this. Yeah, for me, yeah, I'm not sure what would the Haskell program would say, but this sounds confusing to me because this condition involves some kind of operation, and I would put this as just as he said, if the number is smaller. So yeah, I would write it like, I'm curious kind of what others think. You know, do they agree with this? Like you can even prove it. Could we compare like if x is smaller? Wait, okay, that's actually double small number. All right, let's my DSM double small number. My DSM. Okay, let's do it. My double small number. X is, if x is less than 100, then x times 2, else x. All right, that's my double, and his double. His double small number x is, what did he write? If x is greater than 100, then x, else x times 2. What did I write? Where did I get this parse error? His double small number x is if, oh, yeah, if x, like this. Okay, so now we have a type of his double small number is an ord a and num a. AA. So num A, I think num A is a instance of the order like class or something like that, because you can order strings or characters, right? And these are numbers. So I think number is, I think at the second place you put like the lesser or like the instance. Okay, anyway, let's do the my number. My double or a num A is the same, right? And can we compare them? Like my double small number, is it equal to, can we do that? His, no, we cannot just compare. Maybe you haven't applied a function to enough argument. Yeah, we should, my double small number 3, is it equal to his double small number 3? It's true. Guess that we could make a better test. Yeah. Okay, actually this is kind of, yeah, this is what I was saying with the words. You know, the words, how you phrase things, I guess, and this you need to start well, right? I need to start well, because once you move on, if you're not sure, it's almost like you can't type fast. You kind of, you know, you think and then you look at the keys, and so I think it really helps to have some kind of to know how to set words together. Like if I'm gonna say, if I'm gonna express myself like this, and or if you see he wrote the result, he expressed the result at the beginning, yeah, and then he put the condition here that is not the same as the one that he said. So, you know, now we have a very simple case. But what when it gets really complex? What, then you're gonna do it like, yeah. Right here we introduced Haskell's if statement. You're probably familiar with if statements from other languages. The difference between Haskell's if statement and if statements in imperative languages is that the else part is mandatory in Haskell. In imperative languages, you can just skip a couple of steps if the condition isn't satisfied. But in Haskell, every expression and function must return something. We could have also written that if statement in one line, but I find this way more readable. Okay. Another thing about the if statement in Haskell is that it is an expression. Okay. Well, these are all expressions, I think. Yeah, these are all expressions. Like the whole language is built out of expression. That's the most beautiful thing in purely functional programming, is that everything is made of expressions, right? An expression is basically a piece of code that returns a value. Yeah, but it could return another expression in that sense, and then but yeah, then you could say functions are first class values, like functions are values then. Yeah, I guess it depends what you mean by a, what do you mean when you say a value? 5 is an expression because it returns 5. Okay, so if 5, so oh, that's nice. So even a 5 is an expression. So it's not like 5 is a value and there's some kind of expression that returns 5 is an expression. So these are all expressions. 4 plus 8 is an expression. X plus y. Yeah, but this comes to that point. I think you have like well-formed, I think the technical term is well-formed expressions. Well-formed, that are like you cannot evaluate. I'll check that. I'll check that. Like once you're done with reducing the expression to its final value, it has a name, something I forgot. X plus y is an expression because it returns the sum of x plus x and y. Because the else is mandatory, an if statement will always return something. And that's why it's an expression. 39 minutes, all right. If we wanted to add 1 to every number that's produced in our previous function, we could have written its body like this. If we wanted to add 1 every number that's produced in our previous function, we could have written its body like this. Double small number prime. Sometimes they use this prime like a variation of a function. X, if this then else, times 2 plus 1. Yeah, so if you would have to put it in like brackets, so like this. I have a button, so when I sneeze, you can't hear it. So that it will mean like this, right? His double small number plus 1, and now it's his double 3, and returns a 7, right? And if I give it a 1, 4, 5, it returns 1. It returns 7. It doubles the 3. Oh, this is interesting. I'm surprised now. Because it seems to me that it's doubling. When it's really doubling, right? If we give it a 3, it gives a 6, and then it adds the 1. But if we give it a 1, 4, 5, if x is greater than x, then just x. Else. But why it doesn't add 1 to 1, 4, 5? Had we omitted the parentheses, it would have added 1 only if x wasn't greater than 100. Yeah? What do you mean? Let's see this. So else x plus x times 2 plus 1 is and then his double small number. Let's try with 3. 7 and 1, 4, 5. 1, 4, 5. We have the same result. Because it should work like this, plus 1 to the whole evaluation, right? So if x, then x is true. So if I give it a 1, 4, 5, and if x is greater than 100, then x, right? And then it should add the 1, right? So if I give it a 1, 4, 5, no, I didn't even add it. Ugh. Wait, if we redefine this, right? And his double small number 1, 4, 5, I'm gonna get 1, 4, 6. Yeah, that was a typo. See, sometimes you get like these. Okay. Yes, and if we don't add this, we're just gonna add. If we remove the parentheses, then it will be like if x is greater than 100, then just x, right? Because the plus 1 will remain only in this branch. X else x times 2 plus 1. So it will be x times 2, right? Look, x times 2. Otherwise, it remains in the last branch, like this. So his double small number 3, it should output 7. Yeah, it outputs the 7. So 3 times 2 is 6, plus 1 is 7. This took a while now, and I only did like one paragraph. Oh my god. Like I'm gonna be making these videos for like how many years? Maybe in 10 years I will know Haskell. Maybe in 10 years I'll get to monads. No, in 3 years I'll get to monads, and then I'm gonna spend 7 years trying to understand monads, and then I'm gonna know everything. No, then as the comment said, monad transformers. All right, had we omitted the parentheses? Yes, now that prime is at the end of the function name, the apostrophe doesn't have any special meaning in Haskell syntax. It's a valid character to use in a function name. We usually use prime to either denote a strict version of a function, one that isn't lazy, or a slightly modified version of a function or variable. So this prime, what he's saying here, and I know this from Nix. I know this just from Nix, that, you know, like, well, yeah, he didn't, this was not explained here. So I guess people will not know what he meant by this. A strict one is like it outputs everything, even the stuff that you don't need. But if you write it strict, yeah, how can I show this in Nix? Wait. Yeah, I think if this is true, yeah, I don't know now. It will take a while. Yeah, it's like it outputs, like if this is true, then this, otherwise that. And yeah, I'm not explaining this well, but it will come to this, right? The strict one and the lazy one. The lazy one just does not, it just computes whatever you need. And if there is some kind of a result that you do not need, it just gives you a thunk, like kind of a thing that says, oh, there is some code here. But if you write strict, if you want to make it strict, then it will give you the all the result of the function. It will not hide anything from you. So it's almost like eagerly evaluated. Not sure if that's the correct term, not eager or applicative. No, that's something what I heard in structure and interpretation of computer programs. Because prim is a valid character in functions, we can make a function like this. All right. An intro to lists. And he's just doing like, what is this? Conan O'Brien. Yeah, Conan. I remember this. Conan O, that was the guy of Saturday Night Live or something. Brian. Conan O'Brien is what? It's a me. It's a me. It's Amy. It's Amy. What's it's Amy? Conan O'Brien. Conan O'Brien. Conan O'Brien. It's a me, Conan O'Brien. Yeah, I don't understand the point of this. Ah, because you can just use this. You can use this in the middle of a word, like, okay. There are two noteworthy things here. The first is that in the function name, we didn't capitalize Conan's name. So function names, yeah. Function names are not capitalized. That's because functions can begin with upper letters. We'll see why a bit later. Yeah, I kind of made a screenshot of this, right? Pictures, screenshots. Eric, Haskell, naming conventions. Yeah, this thing, right? This thing. So you see this function and argument names must begin with a love case, the lowercase letter. My fun, fun1, arg2, and x prime. By convention, list arguments usually have an s. Yeah. This is, I think this is x is for characters and s for numbers when you have more numbers. And this is, this is for a list of characters and a list of numbers. So like N and S, yeah. Something like N or NS, yeah. And NSS is like a list of lists. You have like a list and then a list, and then A, I think B, and then a list and you're closing. So yeah, it's like a list of lists, a list with a string or like this. Yeah, and types are actually written with capital letters. When a function doesn't take any parameters, we usually say it's a definition. when a function doesn't take any parameters, we usually say it's a definition or a name, because we can change what names or functions mean once we've defined them. Conan O'Brien. Yeah, except I guess a lambda. Lambda. I think I like to say lambda now. Eric Mayer says lambda, and I like lambda instead of lambda, lambda. Once we define them, Conan O'Brien, the string. Yeah, so lambda would start with a name, right? Because lambda is always with a name. Lambda. Like identity X is X, right? But it's not. Lambda would be identity lambda X X, right? Yeah, lambdas. We like lambdas because we can change what names and functions mean once we define them. Conan O'Brien, and in the string it's a me, Conan O'Brien, can be used interchangeably. Also, like the meaning of this is can be used in what's the type of Conan O'Brien? Conan O'Brien has a type of a string. Has a type. I think this is has a type, you say, of string. Okay, an intro to lists. How long was this? 51 minutes. I guess I should stop now. This was so long. Oh my, this was really long. An intro to lists, lost numbers. We're going to do, yes, I'm going to start because here we're going to do all kinds of operators on lists. Yeah, 1, 2, 3. We're going to see how lists are built. And this is indexing string from lists, which is not a great idea, but still, like, you don't want to be doing this. Yeah, it's gonna be interesting. Head, tail, last in it. Yeah, this is fun. Okay, let's just stop here, right? And I'll just make a new one about lists. Yeah, this was kind of interesting and long.